Question 30 asks us to consider the graph that's shown and then determine whether it has an Euler path, an Euler circuit, a Hamiltonian path, or a Hamiltonian circuit. For this type of problem, we know the first thing we want to do is look at the degree of each of the vertices. The degree of vertex A is 1, B is 4, C is 3, D is 2, E is 2, and F is 2. Remember, when we're looking at the degree, we're counting the number of connections that go to that vertex. So in the case of vertex B, we've got 1, 2, 3, 4 connections going to it. Now, in order to have an Euler path, we need to have 2 odd degree vertices. We look at the vertices, vertex A has degree 1, and vertex C has degree 3. So we have 2 odd degree vertices. That means we do have an Euler path, but we won't have an Euler circuit, because the rule for an Euler circuit is that it's going to have all even degrees. Now, looking for a Hamiltonian path or a Hamiltonian circuit, the first thing I'm noticing is that I've got a vertex here, vertex A, which has a degree of 1. It also has a directed edge here. We can only go one direction along that edge. As a result, it pretty much tells us that A is going to have to be our starting point for the path. So I'm going to start off at A and go to B. From B, obviously I can't go to C. I have a choice of going to F or E. My objective, remember, is to get to every vertex once, but only once, so I can't repeat any vertices. So I'm going to go down to F, from F to D. However, at that point, I'm now running into a directed edge, so I can't go that route. Alternatively, I can go from B to E, and from E up to C. If I go C to B, I'm repeating an edge, so that doesn't work. However, the directed edge does allow me to go to D. From D, I can go to F. So with that path, I've been able to go to every vertex once and only once. That means I do have a Hamiltonian path. As I mentioned, since vertex A is a single degree vertex, we're not able to complete a circuit, so there is no Hamiltonian circuit. In question 31, we've got a taxi transportation problem. We've got Emily, Jake, Savannah, and Durham, who are all getting picked up by a taxi and going to the airport, which is vertex A. They have to pass through vertex B, which is an intersection. Now, one of the tricks here is that it tells us that the taxi, first of all, has to start at Emily's house. So that's a key piece, that's going to be our starting point. And then it says they're going to pick up Jake and Savannah in any order. And then after they've picked up those two, then they're going to pick up Durham. So they have to first pick up Jake and Savannah, either Jake first or Savannah second, or the other way around, Savannah first and then Jake second. Then they need to go and pick up Durham before heading to the airport. My first thought when I looked at this problem was that this was going to be a tree of optimal value type of problem. However, it is actually a little bit different from that type of problem, because it's not so much about minimizing the connections between them, it's about minimizing the distance traveled while getting to each of the specific vertices. So it's a little bit different from a tree of optimal value, so that's not going to apply in this case. After that, then I thought, well, maybe it's a Hamiltonian circuit. But it's not necessarily Hamiltonian because you're allowed to go through a vertex more than once. It doesn't say specifically that you can't return to the same point. And there's no specific requirement to cover all of the edges, so it's not an Euler circuit. That leaves us with fairly much a trial and error process to find the solution. We're told we need to start at Emily's house, so I'm going to start off first going from Emily's house down to Savannah's house. Now we have to pick up Jake next, so that means we're going to have to backtrack immediately to Emily's house and then go down to Jake. Now we have a choice. We could either backtrack from Jake's to Emily again, or we could go through B and back to E. However, in doing that, that gives us a total distance of 2.7 rather than 2.3. So we're not going to want to do that. We are again going to backtrack. Now once we've backtracked, we need to go get Durham, and then from Durham, again backtracking to Emily's place, into the intersection at B, and then to the airport. So let's look and see what that adds up to with each of the edges. We've got 2 twice, then we have 2.3 twice, we've got 2 twice again, and then 1 and 0.5. If we add that all together, we end up with a total distance of 14.1. Let's try a different route. This time let's go down to see Jake first, and again we're going to have to backtrack, then down to Savannah. From there we don't need to backtrack this time, we can go straight to get Durham, Durham past Emily's house, Emily's to the intersection, and then to the airport again. So we're going to add them all up, 2.3 twice, 2, 3, 2, 1, and 0.5, which gives us a total of 13.1. Let's try an alternate route. We'll start off with going to Savannah first. This time we're going to take the bypass here over to intersection B, then from B to get Jake, back past Emily's house, over to Durham's house, back to Emily, back to the intersection, and then off to the airport. Adding each of those up, we've got 2, 2.7, 1.7, 2.3, 2, 1, and 0.5, which adds up to 17.2. How about starting off in a completely different direction? This time let's go E to B, B to J, and J back to E. Well, right away by doing that, I already figured out that going this route of 2.3 was shorter than using the path 1 and 1.7. That's not going to be a productive way of starting a new route. How about going from E to J, J to B, B to S, S to D, D to E, E to B, and B to A. So we've got 2.3, 1.7, 2.7, 3, 2, 1, and 0.5. If we total that up, we get 13.2. There are a number of different routes to get there. The shortest route we found, the shortest route is 13.1. Question 32 says Roger wants to install a watering system in his garden. It gives us the distances between each of the sprinklers, which are indicated by the vertices A through G. The pipes connecting the sprinklers are the edges. The number associated with each edge represents the cost of installation in dollars, and we're asked to find the lowest cost to connect all the sprinklers. This is a tree of optimal values type of problem. You'll recall that in a tree of optimal values type of problem, we first figure out whether we're minimizing or maximizing. In this case, we're looking for the lowest cost, so that means we're minimizing. When we're doing the minimizing, we start off by looking for the edges with the smallest values. In this case, from looking at this graph, we can see that the edge from B to G is the smallest value. As a result, that's going to be the first edge that I put onto the graph. Now I look for the next smallest edge, which in this case is from B to E at 105. I add that edge into the graph. Looking for the next smallest edge, I see that it would be 108, connecting G to E. However, in this case, connecting G to E would create a circuit. We're not allowed to have circuits in a tree of optimal values, so we're not going to include that edge. After the 108, the next smallest is 110, which we find here between A and B and D and E. We'll go ahead and connect those two sets of vertices. After 110 comes 112 connecting A to G. However, again, we're not allowed to connect that because it'll give us a circuit, so we don't add that to our graph. After 112 comes 115 connecting B and C. Go ahead and connect them. And finally, the last edge to add in is from F to E. We've completed our tree of optimal values. Now it's just up to us to add up all of the weights that are there for each edge. 110 plus 115 plus 100 plus 105, 110, and 120 gives us a total of 660. Question 33 asks us which of the following graphs contains an Euler circuit. Remember, for there to be an Euler circuit, the degree of each vertex in the graph has to be even. We start off looking at graph A, and we look at vertex A and we see 1, 2, 3 edges connecting to vertex A, which means it's an odd degree, so right away we can say that it does not have an Euler circuit. Graph B, 1, 2, 3, 4, that's even. Vertex B also as even with 2 vertices. However, vertex C we can see is 1, 2, 3, so it has an odd degree, therefore it will not have an Euler circuit. Graph C, same thing. Vertex A is 1, 2, 3, so right away we identify that it does not have an Euler circuit. Graph D, 1, 2, 3, 4. Vertex B has a degree of 2. Vertex C has a degree of 2. Vertex E has a degree of 4. And vertex D has a degree of 2. As a result, we can see that all of them are even. So based on that, we can say that yes, graph D does have an Euler circuit. In question 34, we're asked, what's the chromatic number for this graph? The first step in finding the chromatic number is to look for the vertex that has the highest degree. In this case, we can see that vertex A has a degree of 4. So we'll start off by coloring it first. Now we look for all of the vertices that are adjacent to that one. So all the vertices that are directly connected through a single edge to that first vertex. We can see that vertex A has a direct connection to B, D, C, and E. The only one it's not directly connected to is F. So all the other vertices are adjacent except for F. So we'll start off by coloring B. Now we can also color C because it's adjacent to A, but it is not adjacent to B, so we don't have any conflict there. If I were to color vertex D red as well, we can see we're not allowed to do that though because it is adjacent to B, which is already red. So we can't go red there. Vertex E, however, is directly connected to A, so it is adjacent to A, but it's not adjacent to any other vertex which is currently colored red, so we can color E red as well. We can use a third color now to color D. It is also adjacent to vertex A. Now when we get to vertex F, we can start over again with using yellow. This gives us a chromatic number of 3. Question 35 says, Ms. James is dividing her class into groups and wants to make sure all the students are in a group that will work well together. She wants to create the fewest number of groups and wants to make sure that every student is in a group with at least one other student, so you have to have groups of at least 2. The table below shows the incompatibility of the students. We're asked what is the fewest number of groups Ms. James can make and which students are grouped together. We'll use letters that represent the first letter of each student's name in order to organize our graph. We're told that Amanda can't work with Chris or David or Francis. Bob can't work with David or Francis. Chris can't work with Amanda, Eli, or Francis. David can't work with Amanda or Bob, and those connections are already on the graph. Eli can't work with Chris or Francis. And Francis can't work with Amanda, Bob, Chris, or Eli, and all of those connections are already on the graph. Now let's find the chromatic number. Our first step is to find the vertex that has the highest degree and color it. In this case, it's F for Francis. Then we look at all the vertices that are adjacent to it and start coloring them a different color. I make A blue. I can make B blue as well. It is adjacent. Now if I make C blue, I've got a problem because it's already adjacent to A, so I can't do that. D isn't adjacent to F, however E is also adjacent to F, so I can color it blue. Continuing with adjacent edges, I color C green, and finally I've got one vertex left, and I can start over now with yellow, and I've come up with a chromatic number of 3. However, I haven't met all of the requirements of the graph. If I laid out each of the groups, I'd have one group with 3 and one group that is just one person, so that's not going to work. Let's try another approach. Again, starting with F in yellow, Vertex A and E could be blue, B and C can be green, and vertex D can be yellow again because it's not adjacent to F. In doing so, this graph now meets the requirement. Each group would have 2 people in it, and no people are paired up with people they can't work with. So our groups would be Amanda and Eli, Francis and David, Bob and Chris. In question 36, Sierra is preparing dinner for her friends. The following table shows the different steps involved in preparing and serving the dinner. There are tasks, each of the tasks has a time, and it identifies whether or not there are prerequisites, so whether tasks that need to be completed before that task can get started. We're asked what is the minimum amount of time Sierra needs to prepare and serve the dinner. So this is a critical path type of problem. Start with task A. It has no prerequisites. Task B depends on task A, and task A takes 15 minutes. Task C has no prerequisites. However, task D does depend on task C, which is 10 minutes. Task E also has no prerequisites, and task F depends on task E. Task E takes 15 minutes. Task G has no prerequisites, but task H depends on task G being done. And task G takes 10 minutes. Task I depends on task H, and task H takes 15 minutes. Task J depends on task F, and task F is a very long 90 minutes. Task K depends on 2 things. It depends on both J being completed and task D being completed. Task D is a very quick 5-minute task, and task J is a 10-minute task. The final task is serving the meal. It's dependent on task B, task K, and task I all being completed. Task I is a 5-minute task, task K is 15, and task B is 45 minutes. To find the critical path, we add up all of the paths and figure out which is the longest. A to B and B to L is 60 minutes. CD, DK, KL is 30 minutes. EF, FJ, JK, KL is 130 minutes. GH, HI, IL is also 30 minutes. From this, we can conclude by finding the longest path that the critical path is EFJKL at 130 minutes. Question 37 says, a company has taken on a new project and the table below shows the steps necessary to complete this project. It gives all of the tasks, the time they take in days, and whether or not any of them have prerequisites, tasks that need to be completed before they can be started. The company has enough money to hire 1 extra person to help with this project. Option 1, they can hire someone to help with task C, which would reduce the time it takes to complete task C by 5 days. The second option is to hire someone to help with task E, which would reduce the time it takes to complete that task by 4 days. Given that the company wants to complete this project in as little time as possible, should they choose option 1 or option 2, and how much time will it save on completing the whole project? So this is a variation on a critical path task. So we're going to start off by creating the critical path graph. We start at task A. Task B depends on task A. Task C also depends on task A. Task D depends on task B. Task E also depends on task B being completed. Task F requires task D to be completed. Task G requires task C to be complete. Task H requires that E, F, and G all be completed. Put in the weights for E, F, and G. And finally, Task I simply requires that Task H be completed. And Task H has a weight of 10. Now we have to look at each option and see the impact that hiring somebody to help with a particular task is going to have on the total timeline. So first we want to see where they're proposing hiring somebody. So the first one, option 1, says they're going to hire somebody to help with task C. So here's task C on the graph right here. It says it would reduce task C by 5 days, so that would reduce that 6 down to a 1. The second option is to hire somebody to help with task E, which is here, and it would reduce the time it takes to complete that task by 4 days, so it would take it down to 6. So which one of those is going to be better for us? We really need to understand what is the critical path through this graph. Let's map out each of those paths. So we're going A to B to E to H to I. The second path we need to evaluate is from A to C to G to H to I. Let's look at the weight of each of those paths. First one, we've got 4 plus 5 is 9, plus 10 is 19, plus 10 is 29. The second one is 4 plus 6 is 10, plus 5 is 15, plus 10 is 25. Those are the starting points for us. Let's look as well at the third path, and the weight of that path is 4 plus 5 is 9, plus 4 is 13, plus 3 is 16, plus 10 is 26. As it stands right now, the critical path is 29 ABEHI. If we followed option 2, it would reduce task E down to 6, which would remove 4 from the total of that critical path, which would take it down to 25. So that's option 2. Option 1 reduces task C to 1 day, taking 5 out of that total, which would take it to 20. We can see that of those two options, option 2, which reduces the critical path by 4 days, will have the most impact on the total project because it's affecting the critical path. Reducing the time it takes to do these steps doesn't have any impact on the total time to do the project because it wasn't the critical path. In fact, by making this change, by doing this hiring, it changes the critical path from being across the top to now being the path that goes straight through the center at 26. Now, to answer the question, which option should they choose, option 1 or option 2? The answer is they should choose option 2 to hire somebody to help reduce the time it takes to do task E, because that changes the critical path. It reduces the time in the critical path.